This is part 4 of the series, Proving the Earth is Not Flat. Since the beginning of this series, I said there would be experiments. So finally, in this segment, I am going to show you 2 simple experiments you can do to prove to yourself that the Earth is a sphere. I picked experiments that are very easy and don't require any expensive equipment. I will show you how to do the experiments, and will show you my results, and explain what they mean for the heliocentric globe-Earth model and for the failed flat Earth conjecture. The first experiment dates back over 2,200 years. Aristarchus of Samos, who lived about 310 to 230 BCE, was the first known heliocentrist, centuries ahead of his time, and was a brilliant mathematician and astronomer. He realized that using simple geometry, one could easily determine the relative distances of the sun and the moon. Since the moon's phases are caused by the light of the sun and our viewing angle, he realized that at first quarter and third quarter phase, when the moon precisely appears half lit and half dark from our vantage point, that the Earth, moon, and sun form a right triangle. So if you can measure the angle between the sun and the moon, simple trigonometry will tell us the relative distances of the two objects. Now bear with me on this. There is some math involved, but you will see it's very simple math. First, in Mythbuster style, let's try this on a tiny scale to show how it works. These two objects and the viewer form a right triangle. This angle is 90 degrees, and with a simple protractor, we can measure this angle, which is the viewer's angle between the two objects. In our example, we get 67 degrees. Once we know that angle, even without knowing the distances, we can calculate the ratio of the distances of the two objects. In other words, how many times farther away is object B than object A? I will explain why this ratio is important later. To get the ratio, we simply calculate the secant of the angle, which is the trigonometry calculation for the ratio of the length of the hypotenuse over the length of the adjacent side. I put a link in the description for the explanation of this, in case your trigonometry is rusty. In our example, this comes out to 2.56. So this means that object B is 2.56 times farther away than object A. And since we can measure the distances here, we can verify that the right triangle method is valid by seeing if we get the same result by measuring. We see that the distance to A is 7 inches, and the distance to B is 18 inches. And so, when we divide 18 by 7, we get almost exactly the same ratio, 2.57. So now we know the method works. Try it yourself with any distances. So now let's try it with the sun and moon. To do the experiment myself, I spent about $20 on this angle tool with a digital readout. You can use a simple protractor, but you will need to add some form of pointing device for alignment. Check timeanddate.com or any other moon phase chart and go out on the date of the first quarter or the third quarter moon. It is easiest when the sun and moon are low in the sky, and of course, you will need clear skies. Here, you can see how I lined up one side of the angle finder with the moon. And to save my eyes from sun damage, I affixed a piece of index card on the other side. This way I could move the arm until the sun's shadow lined up straight down the arm, and I could tell it was aligned with the sun. Never look directly at the sun. I did the experiment 3 times on different days and in different locations. My results were very close together, 88.3, 87.5, and 86.1. So let's use the average of 87.3. At 87.3, the distance ratio calculates to 21.2, meaning the sun is 21.2 times farther away than the moon. Now let's see how this observation fits with the flat Earth model. Now, I understand that flat earthers have yet to come up with a map they all agree on. But it would have to look something like this azimuthal equidistant projection map, even though there are, of course, many problems with it. Australia is not wider than the US, for example. But we have to use something, and this is the map most of them seem to agree on. So now I'm going to try to create the best case scenario for the flat Earth model. I will use the maximum possible sun-moon distance and the minimum possible viewer's distance to the moon. So if the moon and sun are both circling above the flat Earth, then we can roughly determine the maximum sun-moon distance allowable in the model. Let's put the sun at its maximum distance from the North Pole, which would be the December solstice, right above the Tropic of Capricorn. And let's put the moon on the opposite side, at its maximum declination, which is about the same latitude. This would make the distance between the two about 15,500 miles. And now, let's put a viewer directly below the moon overhead. Flat earthers seem to agree that both the sun and moon are about 3,000 miles high, so that is what I will use. If you say they are higher, then you are going to have even greater problem explaining why they can set. This is already a huge problem, but I'm going with your model. So now, we draw a triangle and measure the sun-moon angle directly with a protractor, and we get just under 80 degrees. And taking the secant of that, we see that the sun can be at most 5.76 times the distance of the sun. But remember, we calculated it was 21.2 times more distant with our actual observation of the sun and moon. That's a huge difference. And to see why this is so devastating for the flat Earth model, let's see what an angle of 87.3 and a ratio of 21.2, as I observed, would look like on the flat Earth map. This would put the sun way off the map, way below the South Pole. There is no way the flat Earth could work if the sun was way off to the side of all the land masses. And, as it turns out, my number is a little bit low. Aristarchus, using rudimentary tools, measured the angle between the sun and moon at 87 degrees, which is right near the average of my 3 measurements. While his method was correct, his measurement capability was not very accurate. Today, with much more accurate measuring capability, astronomers measure the angle to be 89.85 degrees. This puts the sun about 382 times farther than the moon, and this agrees with several other methods we have today for determining the sun's distance. The number I got is conservative. The more accurate you measure, the worse it gets for the flat Earth model. Remember, I used the best case scenario for the flat Earth model. If you make the observer farther away, or make the sun closer, the viewing angle gets even smaller, but you need it to get bigger. Do the experiment. See what angle you get. You would have to get an angle close to 80 degrees or lower for it to even have a chance of working for the flat Earth model. But you will see it is close to 87 to 90 degrees. If you do this experiment and are still a flat earther, then it's time to admit you are not looking at the question scientifically. The second experiment is called the equinox sun. This is a simple experiment that anyone can do, anywhere in the world. Every 6 months, at the spring or fall equinox, the sun rises and sets exactly due east and west, no matter where you are on the earth. This is due to the spherical shape of the earth and the earth's tilt. At the equinoxes, the earth's axial tilt is sideways with respect to the sun. So on every place on the earth, as we rotate west to east along our latitude, we all see the sun appear due east and set due west. The rest of the year, the sun will rise and set a bit to the north or south, due to the Earth's tilt being toward or away from the sun. A good way to test this is to find a street that runs due east-west and watch the sun rise or set down the street. I did this test on the fall equinox, September 22, 2016, on a short east-west street in Orange County, California. I filmed the sun setting directly to the west down the street. There are some coastal hills here, so it is setting behind them rather than the true horizon, but you can tell that it is angling directly toward due west at the horizontal plane. Allow me to demonstrate why this works on a globe model. I set the globe up with a light representing the sun and the tilt leaning sideways to that light. This is the Earth's position at spring or fall equinox. So we see, as we rotate the globe, viewers along the same longitude cross into sunlight at the same time. This is equivalent to their sunrise. But notice which direction they all must face to watch the sunrise. It is exactly east, because the Earth rotates along the lines of latitude, and this is perpendicular to the sun at equinox. Now let's try to picture this on a flat Earth model. If the sun is circling above the flat Earth, then the direction you see it rise and set at any time of the year, including at equinox, will vary greatly depending on your location. As you can see in this animation, the further south you are, the further north the sun would appear at sunrise and sunset, and vice versa. This is not what we see in reality. There is no way to make the equinox sun work on the flat Earth model. A YouTuber named Dazza the Cameraman recently issued what he called the Equinox Challenge, asking people to do this experiment and post their results. Many have done so. Go to YouTube and look at these, and also try it yourself, and try to find a valid explanation for the flat Earth model. It simply cannot work. For many months now, many of you flat earthers have been telling me I need to do my own research, while you largely ignore all the evidence I have provided in this series. So now it's time for you to put your belief to the test. Do these two experiments carefully and honestly, and then try to explain your results with the flat Earth model. You will see why the flat Earth model simply does not fit the reality in which we live. Only a spinning, sun-orbiting sphere explains all these observations. Thanks for watching.